nanoHUB.org.
Online simulation, and more for nanotechnology.
Thank you all for joining us today for our webinar, Micromagnetic Simulation of Magnetic Nanowires, MNW, using OOMMF to predict heating ability. Our presenter today is Yicong Chen. Yicong is a PhD candidate at the University of Minnesota in the Department of Chemical Engineering and Materials Science. He received his bachelor's in chemical engineering from Oregon State University. His current research focuses on using micromagnetic simulation to characterize magnetic nanowires for various applications. Thank you so much for joining us today.
Thank you, Erin, for the introduction. So my name is Yicong Chen, and welcome to this webinar on using the nanoHUB platform run on the micromagnetic nanowires to predict their heating ability. So first, let me give a brief overview of today's presentation. So first, I'd like to give a introduction to the background information about nanowire and also the nanowarming process. The next step is to introduce a little bit about OOMMF for micromagnetic simulation. And lastly, I would like to go briefly about the actual procedure for using OOMMF on nanoHUB platform. So about the motivation for the nanowarming process, you know that the organs or the tissues for transplant, most of those samples are kept in a very cold environment, which are called cryopreserved. And to rewarm those organs up for use or for transplant, we will need very rapid and very uniform heating. As you can see from this picture, if the heating rate is not fast enough or is not uniform enough, partial crystallization or cracking will be formed, which can cause damage to the sample. By using alternating magnetic field put magnetic nanoparticles inside this field, we will be able to generate very rapid and uniform heating to avoid those damage. And our magnetic nanowire particles can be a very good candidate for this procedure because on this size comparison picture, you can see that the nanowire shown by this small black line is pretty small, which means they're just the longest dimension of the nanowire, which is its length, can be as long as the size of a platelet. This means these particles can be easily injected into the organ and be easily flushing out after warming up the organ and cause little damages. And also the small sizes can enable them to disperse very uniformly if they are properly coated. Also, those nanowires can be very hot, which means they can heat up. They can provide a very rapid heat for the nanowarming process thanks to their shape anisotropy. You can see from those experimental results, the heating rate of the nanowire samples are well above the critical warming rate required for VS55, which is a typical cryopreserved or agent, CPA. And the theoretical limit of the heating rate can be as high as 1,000 Celsius degree per minute, which is pretty high speed, which is pretty rapid heating. So in order to obtain a theoretical heating limit of the nanowire, we will use the following theory. You know that there will be a reversal or a hysteresis loop of any magnetic particles. And we can use the area enclosed by those loops to represent the induction heat loss, which we will use as the heating source for the nanowarming process. You can see on the equation here shows the sample calculation of the unit. By simply using the unit of the x-axis and y-axis, we will have the calculated unit for the area to be watts per gram, which is just simply the same unit as the a typical heating rate called specific absorption rate, SAR. And the area enclosed by the hysteresis loop will represent the heating ability of the nanowire. So by doing, instead of actually fabricating those nanowires, we can use the simulation tools like OOMMF today to run the simulation and generate the hysteresis loop, calculate the SAR, predicted SAR value. You can see that our magnetic nanowire can have a very competitive SAR value as compared to the spions, which are typically which are not typical material used for nanowarming process. So and that's conclude the introduction about the background information of nanowire and also the nanowarming process. Is faster warming rate better for this process? Yes, because to rewarm up the cryopreserved organ, we want it to be very fast because we want to avoid partial crystallization to the organ, which is fatally damaging for the sample. So yes, for this nanowarming of the cryopreserved organ, fast heating rate will be better. Thanks for your question.
What is SAR, S-A-R?
SAR means like a specific absorption rate, which means it's another like direction of measuring the heating ability, like how much heat is absorbed like from the by the sample, and this can be converted easily to temperature per minute, and that's a typical parameter to yes a specific absorption rate, and they do measure the heating ability of a sample in watts per gram, like specific heating ability per mass. You know, watts is like a power unit, and the gram is a mass unit, so it will give a good estimate of the heating rate. Hope this answers that question. Yes, why glycerol? There are like there are a lot of choice of like different cryopreserved agent, and glycerol is just among one of those. And I believe glycerol is less toxic than VS55, and that makes them coming out sometimes as a good cryopreservation agent. All right. So the next part would be, since it was well to run the Micromagnetic simulation, it will be good for me to introduce a little bit about OOMMF. So before I ever go to the introduction about OOMMF, I would like to recommend this useful user guide provided by the developer of this software. You can nearly find any question solved on this manual. The only thing is like it's a little too long, so I will. So that's why I'm going to introduce briefly like a specific procedure for running Micromagnetic simulation. And the webinar today, I would like to share mostly I would like to share based on my own use experience. So I myself is not a code writing guy, which means I have very light coding knowledge, and I'm more used to using the Windows system. And OOMMF does a good job by providing Windows user-friendly interface, and also little coding knowledge is actually needed for running the simulation in itself. So you may have already known that how to use the OOMMF on nanoHUB. I'd like to just maybe reiterate it for you to get access to the OOMMF software on nanoHUB. So if you have your own account on the nanoHUB, which you might already have the link for that, on your dashboard under the My Tool list, you will find, if you have recently used this tool, it will be shown on the Recent tab. Or if not, if you first use it, you can easily search for this OOMMF program in the All Tools tab. And besides the main program, you can also find other useful tools. For example, the generator for MIF generator to generate files for the simulation procedure. And after open the main program of the OOMMF, you will be prompted to a Windows-like desktop, and that's why I prefer this software, because it's very direct. So on this Windows-like desktop, you can find on the left-hand side, you can see this import and export windows where you can upload or download the MIF file or the simulated data. And on the right-hand side, you can see this MNW launch, which I will call it the main windows of the program. So today, I would focus on these three different functions, MNW display, MNW graph, and also OOMMF, which is extensible solver interactive interface. So first, OOMMF, which is the place where you load your file and run your simulation. I will go through this later during the actual steps of the simulation process. The MNW graph function group will enable you to plot the simulated data, where you specify properly the x-axis and y-axis, and all the numerical data will be sent here. You will be able to save and also to see the plotted hysteresis graph in this project. And MNW display is another function group for displaying the magnetic moment snapshot like this. The magnetic moment will be displayed in the form of different arrows. You see here the arrow are pointing everywhere because it's by default the random moment at the starting point. M0 is randomized. Also, there are a lot of functions in this display mode, and I will introduce later. So I've mentioned MIF file. I'm not sure if any of you have heard of this file. It's like a typical text file used for the OOMMF system to run the procedure. As I said, you can, if you have coding experience in C++ or Tcl, you can easily write your own MIF file if you want to. And as I said, if you're like me, are not a programming guy, you can easily find examples provided by the OOMMF itself, easy. They are very useful MIF files, and you can choose to use any part of the block in their MIF file. Or you can use the tools I mentioned in the all tool on nanoHUB platform. They are also very useful tools to generate MIF files. And I will choose one of those tools to show how this will work. For this, for my project specifically, I would like to specify two key factors. The first one is the fact that the parameters specify different materials for the nanowire, and the next one is the geometry of the nanowire. So there are two key factors that determines the material used in the simulation. The first one is the exchange parameter or exchange stiffness, which is A in Joule per meter. And the other one is maybe you're more familiar with is saturation magnetization, MS in kiloampere per meter. And those two are specified for each different material. And next one is geometry. Since we are running the simulation for magnetic nanowire, which I will use a cylinder to represent it, and the size and the diameter and the length can be specified very easily. On the right-hand side, you can see a cuboid, which is called mesh in this OOMMF system, and it is the smallest simulation unit, where we assign the parameter of magnetic property into the mesh, and by summing out of the mesh of the whole sample and minimize the whole system energy, we will find the value at each applet field. All right, here comes to the specific block in the MIF file. First, it determines the geometry information. Yeah, and you can see that here's a block for shape, cylinder. Here's the size, which represented by X range, Y range, and Z range. And then you also need to specify the size for the mesh, like this. And the mesh size should be obviously smaller than the size of the cylinder. And these can all be found either in example or by using the generator to generate the MIF file. And then the next one, it's the parameter need to specify for a material. Take ion as example. You can just simply enter the numbers here for exchange parameter, and then MS. But pay attention to MS. It is because since we have different regions like cylinders and the other universe, like no material, we have to specify different values for those two. And M0 is like the starting point of M, which is should not matter too much for our simulation results, because after apply the external field, the M will change immediately.
Is the heating you mentioned generated from AC magnetic field or DC magnetic field?
Yes, it's from AC magnetic field. And so that's only a prediction from the DC results by assuming a frequency, and we can calculate the SAR. So yes, we are doing the simulation on DC field. Yes, we are performing simulation in DC field, which means we just switch once from positive saturation to negative saturation and go back and generate one hysteresis loop and use the hysteresis loop as our prediction for the heating ability in AMF. And actually, we can run AMF also. So yeah, before considering the frequency, the area enclosed by the DC field is in joule per gram. And after multiplied by the frequency, we can get watts per gram, which is the unit of the SAR. Here comes the question, what sets the frequency of the AC magnetic field? So for this simulation specifically, there's no AC field information because we simply just want a hysteresis loop running in the DC field. But there's another like MIF file which you can also easily find from the examples. It provides like a sinusoidal field which you can enter the AC field information inside. Well, it will be better to have smaller size for the simulation because the finer the better the results, right? But sometimes this will sacrifice the simulation time. So you all need to find the balance between these two. If you want to have a really like good simulation, you would use a very small mesh size. But if you just want to find out like the general property of the particle, you can choose a larger mesh size. But be sure to make your total sample. For example, if you want to use the cylinder, you want to use finer enough. You want to have the mesh smaller enough to actually show the rounded circle, because we want to subdivide the sample as small as enough to maintain a circular shape. Continue with the external field in the MIF file. So for example, if you want to enter external field in millitesla, we can first have this multiplier. And then in this H range function, you can see that there are several columns, 0, 0, 30 to 0, 0, negative 30. This means you have the external field go from positive plus 30 in Z direction to negative 30 in Z direction, and in 300 steps, which means each change of external field is 0.2 millitesla. And similarly goes then from -30 to 30 in the same steps, which close the full hysteresis loop. And that simply finish up one simulation, which is pretty simple. So for the output or the data processing, there are two parts of the output data. The first one is the numerical data which from the MNW graph function, which we will use those to plot the hysteresis loop. One tip is that sometimes if you have a very thin, very fine mesh size and also a very large field applied, the data can be very large, and sometimes it exceeds the memory of the platform that you cannot download directly. So you can use the thin data function to cut the size of the data by 50 or even by 90, as long as the data shape is as long as the data is in good shape. This will reduce the size of the data. And the other part of the output is the magnetic moment snapshot, which is downloaded from MNW display. And these are in .OOMMF extension file. You can either view this in 2D directly from the display, or you can download the OOMMF file. So you can either view it in 2D from the MNW display directly from OOMMF, or using the third-party software called like MNW if you want to view the magnetic moment snapshot in 3D. And here are some sample output data we have already got. Like I have said, here is a collection of all simulated hysteresis loop for nanowires with different material and sizes. And take a look at the ion one. You can see that with the increase of the size of the or the diameter of the nanowire, there is a huge change of the hysteresis loop in shape. And by comparing and here are the collection of the ion magnetic nanowires from 50 to 200. And then you will compare the magnetic moment state just before switching. You can see that there's a big difference between the states here, separating by different sizes of the nanowire. And this can, to some extent, explain the different shape of the nanowire, of the hysteresis loops. Also, thanks to the MNW display function, we will be able to make some movie clips for the whole reversal process. First, this is for ion 50 nanometer. The color, so as I mentioned, the magnetic moment is represented by different arrows, and the color one means the arrow is actually lie in plane, in the XY plane. And white arrows means the moment is pointing up, and then black is pointing down. So you can see that a portion of the nanowire have vortex formed before the reversal. So maybe I can answer that question. What type of reversal it is? It's the propagation of the vortex domain wall that forms during the reversal. And for the color area represent the vortex, yes. So it's in plane. Instead of pointing up and down, the color one means it's in XY plane, yes. And with the increase of the size of the nanowire, you can see the portion of the nanowire forming the vortex becomes larger as compared to the 51. There are more part of the particle forms this colorful region. And if the size is even larger enough, say 200 nanometer, there will be separated different domains. Here you can see. And the reversal process is more complicated, like the outer side switches first and then the inside. You can still see the inside have colorful lines remains. And we will call that a skirmion line reversal pattern. And this it can be also represented by the wasp wasted hysteresis loop, like here. And also, besides the reversal mechanism, I don't know if you still remember, we are running this process for predicting the heating ability of nanowires. And the heating ability can be represented by the area enclosed by the hysteresis loop. And since we have all the simulated numerical data, we can easily use any data processing software like MATLAB or Excel to calculate the area. And here's a sample calculation. Yes, here comes a question. What is the physical origin of the variation of reversal depending on the cylinder diameter? Yes, so here is a theoretical name called critical radius, which gives us like a threshold. Like before, like if the diameter is below this critical diameter, there will be only transverse wall forming, and if it's larger than this, the vortex will form. And if it's even larger, the wasp will be resulted, like the skirmion line will be the main mechanism for the reversal process. What is the gap? The gap between the calculation and real number. After there will be gap because we are ignoring a lot of experimental conditions here, since we are using like the perfect cylinder with very flat tips and very rounded circles. There will be some discrepancy, but since the mostly effective part is the shape anisotropy, which determines the reversal process, we can still have a very good estimation of the hysteresis loop plotted. What generates the heat in nanowire when the cycling through the hysteresis loop? I think it's due to the change of the direction of the magnetic moment that generates the induction. That can be analogous to the induction heat in the circuit. I'm sorry, I'm not sure if it's something related to the phonon energy. So actually, since we are only doing this for DC field, we have to assume a frequency of if we want to put this nanowire in the alternating magnetic field. So at 300 kilohertz is like a very low end of the commercially available OOMMF value. And experimentally measured can show even better heating. Thanks for the, yeah. Because we will have a more rough surface and also rounded tips. Therefore, we can even have a better heating number for the real process. How can we consider the thermal activation in the simulation? Yes, there will be some like thermal flex if you enter the temperature, if you enter different temperature. But unfortunately, I have to say, I only conduct this simulation at 0K. And I can predict that if you have a higher temperature, there will be more fluctuate at two end of the two saturation position. And yeah, here you can see a sample calculation. If we have an assumed alternating magnetic field of 300 kilohertz, by multiplying the saturation magnetization, the area enclosed, 1 over density, and also this vacuum permeability, we can calculate the predicted SAR of 13,000 watts per gram. And we further assume that we are using 3 milligram per milliliter CPA. We will have a estimated heating rate of about 1,000 Kelvin per minute, which you might remember that it's the theoretical limit that we have from the experimental results. And that ends the introduction to the OOMMF for magnetic nanowire simulation. This is my dashboard. And under My Tools, you can see that there are different softwares that I used recently. And if you cannot find those, you can just go to All Tools and search for OOMMF. It will simply get a list to you. You hit Enter. Yeah. Here's the import and export function. And then you can upload any image files you have on hand. And unfortunately, I think you can only upload one file once a file. And then click Oxy here and select it. We will have this. To load the file, you just hit File, Load, and you will see the files we just uploaded. Right? And here you can see all the output data is included here. To actually run the simulation, we will hit first the MNW graph function and set the data table to it. And you'll notice here is step and stage. The step means one simple iteration, and the stage means the smallest change between the external field. For example, if the step of the external field is 1 millitesla, so this stage represents 1 millitesla. And every means like how frequent you want this data be recorded onto this MNW graph function. And after sending the data table to the destination, and you will be able to select the X and Y axis. Since we are going to plot the hysteresis loop, we'll first select BZ, which is the external applied field in Z direction, as our X axis. And MZ, which is the magnetization in Z direction. And one thing to mention is that all of the magnetization has already been normalized, which means they are all divided by the saturation magnetization in this program. And that finished the setup of the MNW graph. And next step, you just hit run, let it go to run the whole process. And to save the file, you click here, Save As. You can either choose autosave or not. The autosave will allow you to save while it's running. And all data, you probably need to select the selected data, because if you choose all data, you will save all of this data that is available on this site, which is a huge amount of data. And if you select the selected data, you will just keep the BZ and MZ data, which are useful for the hysteresis loop generate. And you'll give the name of it. Since this is for ion cylinder 200 nanometer. Can give it. And the file will be in ODT file, like here, for it to be later recognized by the OOMMF to read the data. And that finished the simulation of the hysteresis plot. And I won't, to save time, I won't run will not run the full simulation process. You can try it afterwards. Pretty simple. And the second part is to generate a magnetic moment map. Now we will use this MNW display function here. Similarly, but this time we will send the magnetization data to this part. You can either choose to save each step or each stage. or just sample one state. Like here. Also, you can choose whatever step it should be at. For example, 30 step, hit enter, and relax. Relax means the system will minimize the whole energy to find the minimum point of that applied field. And after you see house here, it means it found the minimum point of that applied field. Yeah. And then you can send it to the graph again. And yes, now you can see that on this slice, there forms the vortex domain wall. Another display window, you can see that you can change some different parameters. The data scale is simply the MS you entered for ion. And this slice means, since now we are viewing from the plus Z axis, the Z slice means you are moving different layers throughout the nanowire. You can also change the viewpoint here. For example, to plus X. Now you are viewing the nanowires sideways. Yeah, unfortunately, this might be too small to show the whole moment map, but you can drag it. Or if you're happy with the snapshot, just click File and save it. Example. And now for the magnetic moment map or snapshot, we will save it as OOMMF file for it to be recognized by OOMMF or some third-party software. All right. And next, since you have already have the data and also have the numeric data and also the magnetic moment data, you can download from the OOMMF. For example, first we'll start with the ODT file. Let's save on your local. And it's already, it can be read by any textbook file. Yeah, you just open the new view, open files, and you can find the latest saved file, .ovf file, and you will see this 3D plot. And to change, if you want to show the cylinder one, you just change the threshold, which is the threshold of the color. That will get rid of the universe. Just leave the cylinder part of your simulation results. And you can choose to display the vectors to better see the direction of the moment inside the nanowire. So it's a little slow. Yes, I think you can see here. You can easily see the vortex formed. And mostly the outer side is switched down while the inner part is still forming the vortex. This is a very good tool to visualize 3D, but you can also view it using the OOMMF itself, but that way you will only get the 2D arrow maps instead of the 3D. I think that ends the steps for the simulation. And lastly, I'd like to show you the generator, a MIP generator tool that is also available on nanoHUB. Again, for my tool, like MIP generator for OOMMF. Yeah. So first, it asks you directly to specify, for example, cube or multiple cubes, ellipsoid or cylinder. You can give the X range, Y range, Z range here, and pay attention. They are all in meter, so you have to convert your nanometer unit here. For example, if we still want the cylinder with a radius of 50 nanometer, and 3 micron. Next, it will ask you to specify the mesh size. Let's just keep it as it is. And next, go to the energy. For example, like uniaxial anisotropy, if you have one. So here, the exchange energy, which is represented, which I just introduced, is the A value in joule per meter. For the ion, which is 0.81 times 10 to the negative 11. Next, you can select from different evolvers. There are 3 different types of evolver you can choose, and you can read the description of these, the description of the difference between each evolver. And it will also allow to select different drivers. There are 2 available drivers. The first one is the time one, which means your data will be based on the simulation time. The next one is called the minimization, which I use for my MIR file, which let you to generate, which let you to calculate the magnetization based on the minimizing system energy. And you can also enter the saturation magnetization here. And also I'm not here. And hit simulate. It will just run a simulation. Or not simulation, but run the coding and gives you the script, which is pretty handy, I think, for generating the MIR file you can use for the simulation. All right. I think that's all I want to share today.
Is it capable to generate MIF file for complex geometry?
Well, for this one specifically, you can only generate cubes, multiple cubes, cylinder, or ellipsoid. But if you want, like, depending like how complex is your goal. For example, if you really want a very weird shaped one, you can use the example available from the OOMMF called image atlas, which you can convert a 2D picture and convert it, like you can draw whatever you want, a shape, and let the OOMMF to convert that into a 3D shape. Maybe one last question, like it says maybe an antenna structure geometry. I'm not sure what antenna structure is really like, but if you want, you can maybe build a cone shape easily by giving like, yes, by using like a image atlas and give different blocks. And I believe you can do that. But I have to say I don't have the right maybe method right by my hand. But I believe the image atlas can do a lot of things. Magnetization in loop. So the saturation magnetization is depending on the material you use. So if it is 17 times 10 to the 5, it should be ion, right? But I'm not sure what do you mean by it is saturated at 14. If it is actually saturated at 14, it should be cobalt instead of ion. So I would suggest you first specify what type of material you can use. So the software will let you to decide what type of material you use. It's like a free method you can use, but it should be determined by yourself. It's not determined. It's like an input of the parameter. So if it is cobalt, I believe it should be 14 instead of 17, right? Yeah, again, this can be like altering by yourself. It's not like a calculated parameter. It's like it's just an input parameter. Hope that solves your question. All right.
Well, again, thank you so much for your presentation today. It was wonderful.